Thank you very much, Mr. Chairman. I assume everybody can hear me and see my presentation. So I'm going to talk to you about, I'll give you a little bit of an introduction. I'll talk about radioluminescence at elevated doses and dose rates. I will then look at something called norm, which is naturally occurring radioactive material and its sensing, and then look at some future prospects, including a couple of extreme situations. So, of course, the popular solution for passive dosimetry are phosphodoped materials. And you can see these in various forms here: chips, powders, rods, etc. They are typically a few millimeters in dimension, which is quite large, given some situations, such as in radiotherapy, where you want to do guided radiotherapy, sometimes at less than a few millimeters. So you need high spatial resolution. Also, the alternative is one of the alternatives is to look at glass, and this is just doped fibers for optical communication. They are doped so that they produce total internal reflection. And if they were perfect, you would only see light coming out at the end, and you wouldn't see light coming from the sides. So total internal reflection, of course, is true at a particular wavelength and is not true at other wavelengths. But what we're trying to do is to do a search for sensitive and robust materials of high spatial resolution, ones that could be immune to electromagnetic interference. So the very latest radiotherapy linear accelerators come together with magnetic resonance imaging, so that electromagnetic we have a range of issues to deal with. The one that I'm showing you here is to try and get from very low levels, environmental monitoring, through to very high levels. So I'm talking about going from milligray to kilogray. And in the milligray range, so you know that you get a couple of milligray by just living on the Earth's surface from naturally occurring radioactivity. And so we tried to create for ourselves something from the optical fibers, and this is called a photonic crystal fiber. You pack lots and lots of small fibers together, and then you melt them down and pull them. So this is just 100 microns across here, and you can see that by doping these individual fibers, that you can get an enhancement in sensitivity. So actually, we have done these sorts of measurements. You can see here. Here's a very famous Bangladeshi name, Professor Kandaka, who works with me. And we've done some work in looking at around a rare earth facility to see if we could detect any contamination. And it works. You can see the difference between 2 months, 4 months, 6 months, 8 months, etc. These are impervious to water, so it doesn't really matter that there's rain, tropical rainstorms, etc. in Malaysia, which is where I'm now living. And at the other extreme, but before I do that, I'll just show you these beads, by the way. One of my ex-PhD students was complaining that the optical fibers were causing her problems with eyesight. So here are 1 millimeter glass beads, the same sort of glass beads you can buy in any craft shop, the sort of beads that women sew onto their dresses. And it's, of course, they are doped because they have they are of different colors. And so we found that these are equally as sensitive at radiotherapy doses to optical fibers. The optical fibers, by the way, that we're using are generally germanium doped. They're around about 4. And here we've looked at doped silica in a kilogray range. The reason that we're looking at kilograys is because in some situations for radiation processing, you want to do cross-linking. You want to produce wires that are resistant to very high temperatures inside motor car engines, and so they're being irradiated to kilogray ranges. And you can see here our optical fibers are giving us linearity up to round about so close to 100 kilogray. So we've gone from milligray to kilogray. So that's a factor of 10 to the 6 change in intensity. So the dosimetry principles, I assume that everybody really understands these. So of course, you can use thermoluminescence, releasing so these are amorphous materials, generally glass. So you've got traps produced by the dopant and also by strain-related defects. This is a two-step process. You irradiate and then you use heat to detrap. Whereas in this situation here, optically stimulated luminescence, you're using, of course, laser light to do the detrapping for you. So both of these are two-step processes. You irradiate and then subsequently, maybe a day later, you do a readout. Whereas in radioluminescence, it's spontaneous luminescence during the period of irradiation itself. So I'm just comparing here TL and OSL, which are this sort of model, against the radioluminescence model. And of course, you will now notice that I'm adopting a crystalline model. And of course, it's true that many of the features of a glow curve that evolve from using an amorphous material are very, very similar to the glow curves that you see in a crystalline model, such as for lithium fluoride or calcium sulfate. So we've adopted this model to try to understand the situation of spontaneous luminescence during irradiation. All right, so we've produced ourselves optical fibers using a modified chemical vapor deposition method, because we initially thought that if we start from a 4 molar percent germanium doped optical fiber that you can buy off the shelf, that if you increase the dopant concentration, you may well get an increase in sensitivity. It turns out that that is not true, that as you increase the dopant concentrations beyond around about 4 molar percent, that retrapping occurs as you detrap, so that actually you're not squeezing any more sensitivity out of it. And ironically, the off-the-shelf commercial fibers are just about as good as you can get. So anyway, so we set up a photomultiplier tube. These are things that gives you maybe 10 to the 7 increase in magnitude of the light. The light that's giving off from these optical fibers is very tiny. And if you don't use a completely blacked out situation, of course, you'll drown out the light that you're trying to measure. So this is a photomultiplier tube, conventional one, with a beam splitter here because we wanted to look at both RL and optically stimulated luminescence. And we have a lab view system to look at our arrangement. So here's the linear accelerator, our optical fiber sensor, around about 100 microns diameter, about the width of a human hair. Here's a PMMA, is a very low response to radiations. And then we have our photodetector here and our counting unit, etc. So you can see this is a linear accelerator. The interesting thing about it is that these are electron linear accelerators that are mainly used in hospitals. They produce bremsstrahlung if you put a target in the way, so a tungsten target, for instance, and produce X-rays in the MeV range. But the important thing is that the radiation is delivered in short pulses, around about 3 to 5 microseconds, so that in around about a second, you've got around about 400 pulses being produced. And so we've looked here at increases in dose rate, and here we've looked at fixed dose rate and different doses. So you can see that we've got very nice response to these. We've got a flat top, which is very, very important, I should point out. We've got almost a square wave where we've got return to baseline is quite rapid. You can see that it's not very, very rapid. Look, you can see here, return to baseline is relatively slow. I'll tell you the reason why I'm saying relatively slow, because right now radiotherapy is given in around about 2 to 3 minutes to give you 2 or so gray. Whereas now this year, they're starting to talk about something called flash radiotherapy, where you can deliver the same dose in around about 150 milliseconds. So timing is going to be extremely important in the future. So if I can look, so you can see here, this is the radioluminescence in counts per second against dose rate and centigrade per minute. And you can see for photons and for electrons, we get very, very nice, smooth and linear curves. And you see here is another of our colleagues from Bangladesh who was working on this during their work on for their PhD. And reproducibility is very good. You can see here that we've just done 10 different irradiations and you get to the same response to within about 1%. And we've been using this device now since about 2016, and we're seeing no reduction in the performance of these devices at these dose rates, which are quite high. I mean, it's 1,000-fold more than you get in diagnostic radiology. Interesting thing is that if you look at aluminium oxide, so this is ruby, you don't see a flat top, and that's because the aluminium oxide materials are used for optically stimulated luminescence, in which you, subsequent to radiation, you read out the decay, which is this one here. So it's a slower decay, and that's what's needed for OSL. Whereas for radioluminescent spontaneous detrapping, you want a very flat response here so that you know that you've got a particular dose. Okay, so diagnostic radiology, you're cutting down now by more than 1,000-fold. So the doses that you get in a chest radiograph is about 0.1 milligray. Similarly for extremities, broken wrists, sprained ankles, etc. And effectively, you're getting a single pulse in the millisecond range. And you can see here, these are different current time products. And you can see that if we look at the different current time products against radioluminescence, again, you get a nice straight line. And so you can be sure that this could actually be used in quality assurance to check that your X-ray tube is actually working as is intended. And this is, we've just used a p-doped, phosphorus-doped silica fiber here, looking at the radiation response against 120 kVp X-rays, which is what you use in diagnostic radiology at these typical times, and at the gate time of about a millisecond. So each of these being captured in a millisecond. And you can see that this is the rise and return to baseline, the characteristics of the RLC generator that's being used. Why are we interested in optical fibers in particular? Well, if you use cylindrical phosphor, of course, you're getting light given off through the sides as well as from the ends. In radioluminescence, the majority of the light is coming out through the ends rather than through the sides. Although, as I mentioned earlier, if they were truly blind to anything other than going through the fiber, you would not see the length of the fiber either. So actually, and later on, I'll tell you that we are now trying to increase the sensitivity by wrapping this with a reflective material. And the best reflective material we can find is one that's got an atomic number of 79, that is gold. And the reason that we're interested in gold is because then we can get photo electron generation to increase the sensitivity as well. So this is looking at the time-resolved measurements. So this is us looking at time-resolved measurements. As I told you, it's about 2 to 5 microseconds. And we're capturing each of these pulses is about 2.5 milliseconds between each of these pulses. So we can do this, and we know that even though there is a slow return to baseline, relatively speaking, it's good enough for conventional linear accelerator applications. Whether it could be good enough for flash radiotherapy, where you're doing this 150 milliseconds, is a question that we're trying to resolve. And we're trying to get materials with the faster response time than these here by working with the University of Shanghai. But at the moment, we've not got into that. Okay. Just want to show you something interesting. Of course, the PMMA is also giving a response, and that's what this orange peak is showing here. But this so-called STEM effect is not only the response from the PMMA, but it's also Cherenkov radiation. So Cherenkov radiation is very, very rapid. It's only there for as long as the beam is on. So each time you're switching on and off very, very rapidly. So in fact, this may well be the clue to us being able to cope with the flash radiotherapy dose rates. I now go to the other extreme, that is norm in oil fields, naturally occurring radioactive material in oil fields, and the oil and gas industry are having problems with this material. There's uranium and thorium in the earth crust. They remain in situ, but the radiums are soluble in water, accompany the well fluids up the pipelines, Radon gas also is there, is very mobile, and you're seeing it coming out further along in the crude oil storage tanks, etc. So the radium is sparingly substituting for barium, strontium, calcium in the scale and the sludge. And so we want to look at the problems that you can get with that. And what kind of problems are we talking about? These are separators, by the way. They separate out the fluids from the gas from the crude oil. The problems are that this is scale formation. And because these are radium, they're alpha emitters. If you try to clean them using mechanical methods, then you'll produce dust, and then you'll inhale, etc. And there's exposure to internal radiation. And just to show you, this is us doing measurements on a whole lot of oil platforms offshore. This is natural radiation levels. This is the radiation levels in a separator. Now you may say, oh, this is very small, but we're not dealing here with a few grams of material. We're dealing with many tons of material up at this end. So actually, we want to have Atomic Energy Licensing Board notification levels like that in Malaysia. That they want to know whether anything is more than 0.5 microsieverts per hour. Background is around about 0.1 microsieverts per hour. So we need something that's very, very sensitive. There are very sensitive devices like this one I'm showing you here. I'm just checking my time. You can see here that, okay, that you could actually put this down a little bit of the way, but you couldn't do all the way along one of these that are more than 10-meter long tubes. And of course, if you have this problem like this, where you can't measure anything at all other than putting it down, having something that's very, very fine, like our silicon fiber materials. And of course, the separators are extremely dangerous because there's the gases in there, hydrogen sulfide, etc., killer gases, are extremely dangerous, and some of the gases could be explosive. Ours is just a light system. There is no electrical connection at the business end, so we could actually do surveys inside here before anybody goes in there. And we're trying to look for a traffic light system. Is it contaminated or is it not contaminated? You might think that this is easy, but actually this is the reality in our oil and gas stockyard with many of these there. And so we think that we can actually use a system based on the silica fibers to actually inspect these well before you actually have to pull any of them out and do these extra measurements like this. So we're looking now not for a box device, but a minified device. So we're looking for something that's handheld. So we're going to go from a photomultiplier tube standard to a silicon photomultiplier tube, the so-called avalanche detectors that can be operated on a 7-volt battery at this end. So I just want to show you that we want something also that's much more productive in terms of light yield. So we've used lutetiummetry and ortho silicate cerium doped materials now in our latest ventures. This is monazite, which is a tailing from the tin mining industry. And you can see this one here is giving us around about 48 microsieverts per hour using a handheld device. We've looked at monazite, and we looked at xenotime, which are again discards of the tin mining industry and rare earths industry and so on. You can see that we're easily able to measure 48 microsieverts per hour. We're easily able to measure 20. This big fluctuations here is because initially we didn't put enough effort into masking from the light that was being produced in daylight. So we've now been able to, by the way, this is just us tracking our GM survey meter against our fiber optical coupled device. And you can see that they're tracking each other very, very well using a cesium-137 source. This is our latest attempt now with everything blacked out extremely well. This is our sensor. There's about 20 meters of cable here. When we took the scintillator away, this is what we get. When we put the scintillator back on, there's no other radiation source other than natural background here. This is what we're getting. So we can measure 0.1 microsieverts per hour. We're going to try much harder with this to reduce this amount of noise. Other potentials, you can look at contaminated land surveys, and here's the IAEA harnessing drone technology. and we think our system is sufficiently light that we can put this onto drones, and we can use telemetry.
Excuse me, Professor David Bradley.
Yep.
You have 2 minutes to.
Okay, I'm very close to the end now. Yeah. So here's the extremes that I've talked about. This is a plasma device. It's a little electrical storm. So each time that you produce a spark, you produce X-rays, or if you can use a gas, you could produce neutrons. But this is nanosecond timing. So you can see our present system is very, very poor. You just captured 2 points on this peak. This peak could be way up here for all we know. So we really do need to be able to have much faster, fast timing arrangements. And the Italians are starting to try and use this to try and do radiobiology at flash dose rates. So we want that. And this is at the other end, using an electron beam processing facility that is giving out those kilograys that I talked about earlier on. This is us, and I'll not look at the spectroscopy. This spectroscopy is showing us variations in the hydroxyl content of the material. But here you can see at 2 particular wavelengths, we're getting quite nice linearity. Each additional milliamp is giving an additional kilogray in this device. So we know that we are doing very, very well. We've gone from 10 to the 9 change in magnitude, and we know that we still have functioning devices. So thank you very much. What we think we might end up with in the future is something where you can actually have something that's just on your wrist to actually monitor what's going on at the fiber tip end. Thank you very much for listening to me.